Titration in chemistry, what do we mean by it? How do you do it? What does all the terminology mean? And what are the calculations? That's what we're going to be talking about in this episode of the Chemistry Made Simple podcast. Hello, welcome to the podcast. If we haven't met before, I'm Matthew Macario. I'm a coach, mentor and tutor for chemistry students like you. And I make this podcast to help you get from point A to grade A. Follow this episode, subscribe to the channel, and let's get on with today's episode. We're going to be talking about titration in chemistry and what it is. What am I going to teach you today? What are you going to learn? Firstly, we'll define what is titration, what's it for. We're going to talk about what types of titration you're going to come across at this level. We'll talk about the different terminology that gets used, the different words that can be quite unusual. You may not have come across many of them before. Some of them are quite unique to titration. We'll talk about the apparatus that's generally used in titrations too. We'll talk about how to use it. In other words, how do you do the titration? And then we'll talk about the calculation, which is the key thing at the end. The whole purpose is to enable you to do that calculation. So firstly, what is titration? Well, it's an analytical technique. It's one of many analytical techniques in chemistry. It's a part of the analytical chemist's toolkit. It's there as a way of measuring the concentration of a sample, the concentration of a substance in a solution. For example, we can use titration to measure the concentration of acid in an acid solution by titrating it with a base solution of known concentration. And as we go through this episode, we'll expand on exactly how we do that. So what types of titration are you likely to come across? Well, I just mentioned that we can use titration to calculate the concentration of an acid by using a base of a known concentration. So that's one way of doing an acid-base titration. You can also do it the other way. You can have a sample of base that you don't know the concentration of and do a titration with an acid solution of known concentration and find the concentration of the base. So you can do acid-base titrations in either direction to find the concentration of an acid solution or the concentration of a base solution. The other type you're likely to come across is redox titrations. Redox is a word we use to describe reactions where something is being oxidized and something is being reduced. And actually, in any reaction where something is being oxidized, something else is being reduced. In chemistry, neither of those processes can happen in isolation. So in redox titrations, our sample that we need to calculate the concentration of maybe something that can be oxidized, and therefore we can titrate against a solution of oxidizing agent that you know the concentration of. And in that case, the reaction happening in the flask is the sample being oxidized and the oxidizing agent being added is reduced until all the sample substance is reacted and the endpoint is reached. And of course, we can do the alternative version of a redox titration. Our sample might be something that can be reduced, and we would use a solution of known concentration of a reducing agent to react with it to do the titration with. So let's talk about some phrases, some words, some terminology that you'll come across. And sometimes you might have had these well explained to you, but often I find students are either just expected to know or to find out for themselves. So the first one we're going to talk about is indicator. The indicator is a reagent that changes colour. It has a very clear colour change, and that will indicate when all the sample compound has been reacted. That's when the colour change happens. An indicator substance is chosen on the basis that it has a clear colour change, and that colour change happens when the reaction is completed, when all the sample substance is used up. Examples would be using methyl orange indicator or phenolphthalein indicator in an acid-base titration. It changes colour at the point when neutralization has occurred. The indicator substance doesn't interfere with the reaction itself, it just shows up when the endpoint is reached. It's important to note that you don't always need an indicator. Some reactions are self-indicating. We often use substances that oxidize that also happen to have a distinct colour change when they're reduced, and therefore it's easy to see when that change is no longer happening, when the endpoint has been reached. So For those, there's absolutely no reason or use to add a further indicator solution. Another word you might come across is aliquot. The aliquot is just the portion of the sample that's used for the titration. This is the amount that you pipette out from the bigger sample, usually from the quantity that was made up in the volumetric flask prior to starting. For example, if you pipette a 25 milliliter sample from the volumetric flask, that portion that you pipetted out is the aliquot. The aliquot is what you pipette into the flask and what you use for the individual titration. You'll definitely come across the phrase endpoint. It's the most important part of any titration. It's the moment in the titration when you've got to the point where you've reacted all the sample compound in the flask, but no more. You've got to exactly the endpoint. You've just got to the finishing point where all the substance, the solution you've added from the burette, is that reacted completely with all the sample substance in the flask. And at that point, there will be the colour change because there's an indicator present or because this is a self-indicating reaction. Another phrase you'll come across is titer. This doesn't mean titration. It looks like it should do, doesn't it? The titer is actually the volume that you'll read off the burette, the amount that you added from the burette to reach the endpoint. In other words, it's the volume of the reagent that you require to reach the endpoint but not exceed it. So each time you do a titration, you'll need to note that volume. That's really important to note down. That's really important for the calculation. And for each individual run of that titration, you will write down that volume, that titer, just by reading it from the burette. You may hear the phrase volumetric or volumetric glassware. And this is a word that broadly describes the group of specialized glassware that we're using for the titration. It's the glassware we use for high accuracy measuring of the liquids of the solutions. We will have a closer look at each of these in a moment or two. The ones we're going to look at are the volumetric flask that you use to make up the sample to a known volume, and the burette that you will use to measure the volume of the standard, the titrant, that you add in the titration. And that brings us to talking about what do we mean by titrant or standard solution. These are the same thing, they're just different phrases for it. This is the reagent solution that you put in the burette, the solution of the reactant that you use to measure the concentration of the sample substance. You do need to know the concentration of this substance, of the titrant, and that's why it's sometimes called the standard or the standard solution, because it has that standard or known concentration. Now we're going to talk about some of the apparatus that we use in the titration, and we'll start with the volumetric glassware, the volumetric flask. This is the vessel that you'll use to prepare the exact volume of the sample solution, and also you can use one to prepare the standard solution as well. These flasks have a flat base. The lower part of the flask is quite bulbous, coming to a tall neck, which has a stopper in the top to seal it. Partway up the neck there is a line marked, and that line is the point at which the volume should be made up to in order for the solution within it to be the exact nominal volume that the flask is intended to give. For example, a 500 milliliter volumetric flask can be used to make up the sample or the standard to exactly 500 milliliters, but only if the flask is topped up to exactly that line with the water or other solvent that is being used. It's important whether you're preparing the sample or the standard that once you've put in the volume to the exact amount, that you do stopper the flask and you do very thoroughly mix the flask. That's the way that the concentration of the substance within the flask becomes uniform, so that when we take a sample out of it, it is representative of the whole concentration within the flask. The next piece of apparatus that you use is the pipette, and the pipette you will use to accurately measure and transfer the aliquot out of the volumetric flask and into the conical flask that you use for the titration. If we look a little closer at what a pipette is like, so a long glass tube has a pointed tip at one end, usually has a bulb partway up the tube, and the other end of the tube doesn't come to a point at all. It's a smoothed off glass tube, and that's the end of the pipette. that we attach the filler to make the withdrawal of the sample from the volumetric flask. Between the non-pointed end and the bulb, there is a line marked around the pipette, and that is the fill mark. That's the point that you must fill the pipette to exactly in order to withdraw the volume that the pipette is intended to withdraw. Another piece of apparatus we'll use is a burette. A burette is used to gradually add the titrant or the standard reagent in a controlled way to the flask that's got the sample in. So you will use this to add the titrant, the standard solution, to the flask and monitor the reaction that's happening until you reach the endpoint. A burette is also volumetric glassware. It's a tube that has volumetric graduations marked up the length of the tube. The lower end there is a stopcock, and then the tube continues to reach a point at the bottom. The stopcock is what you will turn to open and close the valve, if you will, to allow the titrant out at a rate that you are controlling, and to stop it when you need to stop when you've reached the endpoint. When you've reached the endpoint, you'll use the graduations to enable you to know how much volume was added. You'll calculate the difference between the graduation that showed before you started the titration and when you finished the titration, and that difference will be your titer for that run, for that titration. We also use a burette stand with a clamp, and this sometimes gets called a clamp stand or a retort stand. You may have heard or used those phrases too. It's usually a metal or wooden device. It's just a vertical stand with a base. It will have some sort of clamp partway up that you attach the burette to, and it's there to hold the burette because gravity. It's important when you use it to hold up the burette that you adjust the clamp such that the burette is suspended exactly vertically. It's not leaning to one way or the other, it's exactly vertical. And that's because you'll be creating errors in reading the volume of the graduations if the burette is not perfectly vertical. Finally, you're going to use a white tile, and you'll put this underneath the flask. That is simply there to help you see the colour change at the endpoint. Nice clear white background just makes it a lot easier to see exactly when the endpoint is, and it's really important to know exactly when the endpoint is, because that is the whole point of doing the titration. If you're not going to see it accurately and stop at the right point exactly, then you're not going to get the right volumes, and therefore you'll get incorrect information into the titration. So how do you actually do the titration? So you start by measuring out a known volume. So you use the pipette to measure out a known volume, the aliquot of sample. And we're going to add indicator to the flask if it's a titration that requires indicator. So we're obviously assuming that we've already prepared the sample solution. We've made it up in the volumetric flask, and that's where we're going to take our aliquot of sample from. We've already got our standard solution, our titrant, and that is set up in the burette ready. And now you've pipetted out the sample or the aliquot that you're going to use in the flask for this particular titration run, and you've added the indicator. And now you're going to gradually add the titrant from the burette into the flask. You're going to do this with swirling of the flask. You're going to note the colour change. You're going to slow down as you can see that colour change becoming more consistent until the point where you see the colour change stay. It doesn't change back again at all. As you were approaching that point where the colour change becomes permanent, you need to have been adding the titrant drop-wise, just one drop at a time. It is just one drop that adds the final amount that reaches the endpoint. And of course, stop as soon as that endpoint is reached. Don't add any more at that point. You need to make a note of the volume of reagent you've added from the burette. If you started with the burette volume and not on exactly the graduation of 0, then it's simply a case of reading off what the volume is when you finish. If you didn't start with it on 0, you just subtract the measurement before you started from the graduation measurement when you finished, and that is your titer for that run. And then you're going to repeat the titration. You usually do a rough version, the first one, just so you've got a good idea at what volume the endpoint is reached. And then you will repeat the titration at least 2 more times so that you get titer values that are very close to each other. On your repeated titrations, you should be getting titer values within about 0.1 or 0.2 millilitres of each other. So we need to do a third one if the volumes from the first two, the titers from the first two, are not within that close value to each other. You'll also need to deduce the balanced equation for the reaction, because you'll need to know the mole ratio in which the titrant and the sample substance react with each other. And then you do the calculation. That is the really important bit. That's the bit that is going to tell you what the concentration is at the end. Now we'll come to the calculation. I'd like to say this is the most important bit. Actually, it's all important. It's really important to do every bit of the titration process as precisely, as accurately, as carefully as possible, making all the observations and noting down the titers as you go along. Calculation is really important because this is the thing that turns your observations, the volumes that you've noted, into the concentration, which is the whole purpose of doing this. So this is not necessarily the most important, but this is a fundamental requirement of doing a titration. What do you need to know in order to do the calculation? You'll need to know the balanced equation for the reaction and write it down. If you're doing this as an exam question, or if you're doing this as a write-up, as a practical that you've done in a lab, then write down that equation. You'll need to know the mole ratio that the reagents react. That's simply what's the mole ratio that the two reactants react at. And you'll see this in the balanced equation. That's why it must be balanced. The other things you need to know is what was the concentration of the titrant, the solution of substance that was in the burette, and what was the average titer, the average volume that was used in your titration runs. Once we have those, what do we do with them? Well, step one is to calculate the number of moles of titrant substance. This is fairly straightforward. The number of moles equals the concentration in moles per decimeter cubed of that titrant solution times the volume. It's important to realize because the concentration is in moles per decimeter cubed, you need to quote the volume in decimeters cubed. You will have noted the volume from the burette in milliliters or centimeters cubed. So you need to divide that titer value, that average titer value, by 1000 in order to get how many decimeters cubed it is. Really important, state what the substance you're referring to. You can't just say moles from the titration equals this. You need to say moles of what. And at this point, it is the titrant substance, the substance that is in the burette, not the sample substance. Next step, once you have the number of moles of titrant, is to state the reaction ratio that the titrant substance and the sample substance react with each other. Then calculate the number of moles of the sample substance that were present in the flask. Not in the whole sample, but in the flask, in the aliquot that you pipetted out. This is simply the number of moles of titrant that you just calculated in the step one, times the ratio factor. Sometimes that's 1 to 1, so you're actually multiplying it by 1. It's the same number of moles. But if the titrant and the sample substance don't react in a 1 to 1 ratio, you need to use the ratio factor there to calculate the number of moles of sample in that aliquot. Just to be very clear, that's the number of moles in the pipetted volume in the aliquot that you took from the bulk sample. Again, state the substance you're referring to. You can't just say number of moles equals this. Number of moles of what? In this case, the sample substance. So state what that substance is. The next step is to calculate the total number of moles of sample substance. What's the number of moles of the sample within the bulk sample that you pipetted from? So this is in the volumetric flask. And that number of moles is the moles in the aliquot and the titrated volume multiplied by the total volume divided by the pipetted volume. So if you had a 500 milliliter volumetric flask that you'd made the sample up in, and you'd taken a 25 milliliter sample, you pipetted 25 milliliter aliquot, then this calculation is the number of moles that you calculated in step 2 times that 500 milliliters divided by 25, the aliquot volume. At that point, you also need to calculate the concentration of that sample. That is simply this total number of moles we've just calculated divided by the volume in decimeters cubed of that volumetric flask. So if our volumetric flask was 500 milliliters, that's 0.5 decimeters cubed. Our calculation to get the concentration is the total number of moles divided by 0.5 decimeters cubed, that total volume. And that gives us our concentration of the sample substance in moles per decimeters cubed. At that point, you may need to do some further calculations as well. It depends upon exactly what the question, what the task was. There may have been a bit of a story in the question, in the task, about how the sample was prepared, about whether it was contaminated, and maybe you need to work out what the percentage purity of the sample substance was. And there's numerous other possibilities, scenarios that may be the story around the question that you need to take into consideration. Obviously, you'll need to consider what those are based on exactly what the scenario given to you in the question or the task is. So what have we talked about today? We've talked about what is titration. It's that analytical method to work out the concentration of a sample. We've talked about what the terminology around it is, what the apparatus you use, how to do the titration, and how to do the calculation. I really hope that's been useful to you. If you have further questions about titrations, about a specific titration or titration question, then please do feel free to get in touch. I'd like to hear from you. And you can do that by contacting me on my email. That's matthew@chemistrymadesimple.net. You can also DM me on my Instagram, and you'll find me at Chemistry Made Simple. And thank you so much to my patrons for supporting the podcast. It really does mean a lot. If you are a patron, contact me there. That's a good way to contact me too. If you prefer to leave a short voice note, you can do so. And that's at my website. That's chemistrymadesimple.net/voice note. I'll show all those links in the details below. If you found this episode to be useful, then please don't keep quiet about it. Share it with someone in your class. Share it with a friend. Let another chemistry student know about it who could appreciate it and who could benefit from it too. That would really be appreciated. Thank you. Don't forget to subscribe to this channel too, so you don't miss out on the next topic as well. And speaking of the next topic, I look forward to seeing you in the next episode. And until we meet again when I publish that, look after yourself and goodbye. So here's those details again. Don't forget to subscribe to this channel. You can also leave me a voice note, contact me on Patreon, DM me a message on Instagram, or use my email address. I look forward to hearing from you, and I will get back to you.